I've known Steve for about 20 years now, and Steve, more than most people on the planet, has been in a unique place to help drive innovation and to watch as other people try to drive innovation and be sort of up close for the successes and the failures of those innovations. Steve has gravitated to the harder problems and has seen probably more of the fat tails of innovation on the positive negative side than anyone else I know. And Steve is going to talk to us today a little bit about what he's seen and some thoughts about how innovation can happen, does and doesn't happen, and relate it to some things that I'm personally interested in about evolution. I hope you guys will find it as interesting. Please welcome Steve with me.
Thank you, Astro. What he may not have mentioned is that we used to sleep together, which is we were in the same undergraduate dorm back in undergrad, and many stories there could be had in Q&A if you really want to get to know Astro. But he's obviously a pretty special individual. And it's an honor for me to be here today, addressing both people here in the room and those out in TV land, as we used to call it back in undergrad days, when it literally was, analog TV streams. What I hope to share with you today is part of our enthusiasm for the future, as embodied in our views learned from many entrepreneurs and visionary scientists that we've met with over the decades on what the future portends in terms of technology trends, the major forces shaping our lives, and some of the underlying dynamics of how we get to those futures. As Astro alluded to, what I hope to spend a fair bit of the back end of this talk discussing is the dichotomy of design and evolution. Different processes of building complex systems, be that code, synthetic biology, or nanotech, in various futuristic visions of the big, interesting artifacts of the future. How will we build them? And there's a grand engineering challenge, I think, that remains there in that sort of open question of how best we can build things that transcend human understanding. I will try to also maybe make some passing references to organizational design, maybe just one slide on that, as it applies to Google. For those who read my abstract, I sort of give a nod to that. And also when Astro and I were brainstorming over lunch a few days back and led him to think, hey, maybe I should be brought in for a tech talk, it was a wide range of topics we were talking about. And so I'll probably seem a bit scattered, which is appropriate for someone like me because, I think I found the perfect career for someone with ADD, which is you get to meet with a bunch of interesting entrepreneurs, hear their pitches, and then move on to the next one. And so do take, of course, with a grain of salt, everything I say as a pattern recognizing generalization across many smart people who actually have original ideas. And what I'm sharing with you today is perhaps a synthesis or catch-all of some of the patterns we're seeing across those ideas, as opposed to, scientific work. I mean, venture capitalists don't directly contribute to the economy. If anything, we help lubricate those who do. So with that preamble, let me just mention some of the things I'm going to talk about. I'm going to start with a generalization about innovation and disruptive technologies in general. Move on to how that is now intersecting energy markets, just because of their sheer trillion-dollar size. This, I think, is an important economic driver for why many of these trends are important to industries for which they may not have been as important before. And then end with that topic, because I think it'll naturally segue into it, that many of the new powerful capabilities we have today open really important questions on how we build these systems. Okay, one quick overview on innovation and disruption. From all the business plans we're seeing more innovation than ever before. Probably no surprise there, but at least I want to say it because in its state of economic tumult, that may not be obvious. But the nature and quality of that has changed dramatically over the last decade. It is increasingly globalized. That Uber trend is not reversing. The companies we invest in today sell to international customers day one. 10 years ago, unbelievably, we did not see business plans from non-US companies. If you can just ponder that for a moment. Just 10 years ago, we not only had not invested in a single non-US company, the companies we invest in, those startups, only serviced US customers. The only time they looked to a European or Japanese customer was about the time they were going public. This was software companies, internet companies, if you will. Remarkably different today. The vast majority of the wealth created in the last 10 years has been outside the US for us. And there's reasons why those network effects over the internet reinforce the globalization trends. Entrepreneurs can be anywhere. They can service customers globally with lower transaction costs than ever before. We think these are mutually reinforcing. So that's just a sort of philosophical preamble. The one and only slide I'll show about DFJ itself, for those not familiar with what is this firm I'm referring to, I work for a venture capital firm. We focus on early stage startup investments, and maybe the most unique aspect of our structure is that we have a distributed set of partnerships. You could think of them almost like franchises in a way, or more like a pre-war Japan Zaibatsu, where every one of these entities has cross-linked equity ownership in the other. So they want to see each other succeed. They want to, in a sense, what we've tried to instantiate is a repeated game dynamic where everyone knows they're in business together for decades, and so therefore we help each other. It's quite as simple as that, and it allows us to scale horizontally across the planet more easily than we otherwise could. In aggregate, there's about $6.5 billion under management, which for the venture, for an early stage venture firm is large, but for any one of these funds, it's a small, reasonable pool of capital. No single fund is $1 billion in size. Okay, innovation. Let me start with a thought experiment, just in case you're sort of digesting and half here in terms of engaging with what I'm saying. I want to pose a question to everyone in the room, which is think of the most important company 20 years from now, and actually try to pick a tangible example in your mind, so that when I sort of make the next statement, you can judge it based on what you're thinking of. So pick what you think will be the most important company 20 years from now. It could be judged from, presumably, the one that's on an incredible growth trajectory, that's changing the world, and that people generally think is the most exciting company on the planet, like Google was, or maybe still is. So 20 years from now, what is it? Is it Google? So you have something in mind, hopefully. I'm willing to bet against everyone in the room and everyone out in TV land. Even money. And actually, anyone wants to take me up on this bet, we can do a long now bet and actually bet real money on this. Then I'm willing to bet every single one of you is wrong, not even knowing what your guesses are. And that may seem cheeky and, I don't know, a stunt, which it is. And the reason is that company doesn't exist yet. I'm willing to bet on a new entrant that doesn't yet have a name over all existing companies someone could think of today. Looking forward, that may seem like a claim. Some of you may agree, oh yeah, of course. Others may say, well, that seems a bit cheeky. But in retrospect, it's always the case, right? In retrospect, we realize the new, the important, the vector of change in the world, the vector of disruptive change always comes from new entrants, never from incumbents. It's a variation on Clayton Christensen's Innovator's Dilemma. But that bet, looking forward, people tend not to apply it as often. You could ask who's the most important business executive 20 years from now. If you don't want to think about companies, you get the same answer. There's a variation on the same theme. Imagine you saw a parade of every startup that we see. We got about 50,000 business plans a year. And let's say they could somehow encapsulate in a short pitch whatever they do, and they present to this audience their new idea of how they're going to change the world. Then imagine we did a popular vote as a policy on which one we think is the one we'd want to invest all of our capital in. Again, that would be the wrong selection process. I'd be willing to bet against whoever wins a popular vote in any investment domain of startup ventures that are trying to change the world. Instead, what you should look to, the one you'd want to invest in, is the one where maybe 5-10% of the room thinks it's brilliant and the rest think it's completely idiotic. That is exactly the kind of company you want to invest in. Because if it's obvious to the majority, right, it's not revolutionary enough to change the world. And this is a truism that in retrospect, of course, makes sense. Despite what venture capitalists will say today, in the moment, they laughed at eBay, Hotmail, Google, and just about every company that has, in fact, changed the world. At the time of their founding, a good idea is generally not regarded as such by the average. Some general points on innovation. Now, I've qualified innovation as disruptive innovation, distinguishing it from the sustaining innovations that big companies do all the time and they're very good at, right? Disruptive innovation is what really matters. And why do I focus on that? Well, you can ask yourself the question, if it weren't for disruption, why would any startup ever exist? And I would contend that they wouldn't. That if you have market stasis, predictability, the big get bigger, the rich get richer, and the new entrants have no chance. They don't have brand, they don't have capital, they don't have distribution relationships. And you can look to old crusty industries like, aluminum powder. It is very difficult to compete with Alcoa, not because they make better powders, it's because the distribution channels have been co-opted for so many years. They're not about to give you a chance to the new entrant, even if you have better pricing. So it's an interesting thing. Where does disruption come from? Well, there's periodic unpredictable sources, such as privatization of industries, deregulation of industries, right? When they exist, we're all over it for short periods of time, but we don't build an investment thesis that spans decades on privatization or deregulation. It's hard to find the next one. You might be waiting a few years for the next interesting opportunity. You certainly will scanning the planet for where the frontier of that sort of market deregulation takes place. Another is a new channel distribution, right? For those maybe 3 or 4 of you in the room that might remember Dell versus Compaq in the old days competing, and how it seemed almost written in stone that Dell would take the business from Compaq due to channel conflict. The fact that Compaq sold through a distribution channel that couldn't be revoked, kind of like automotive companies in the US have dealership contracts they cannot revoke. It makes it easier for new entrants who sell direct to bypass that. The internet was the greatest new channel distribution we've ever seen in terms of power and scope. That impact has barely been fully felt. The next one seems to be mobility as a way to reach customers more directly. I couldn't tell you what the next one is. In Q&A, please tell me if you think you know what the next great channel distribution is to reach customers, because that would be a good investment thesis for us. But there is one, the whole buildup is there is one you can count on every year, every decade, and every century. So that 50 years from now, even 100 years from now, there will be venture capitalists and there will be startups. And the reason is because of technology being nonlinear in its pace of change. The accelerating pace of technological change is the fundamental perpetual driver of disruptive innovation. It's why new entrants continue to exist and why they continue to enter the market and why venture capital by proxy exists. That's why we're enthusiasts for it. Okay, well, what's the most canonical example? Of course, Moore's Law, right? And this is Gordon Moore himself. Oh, the graph doesn't come out so well on the screen, at least from my angle. But he's a happy Simon fisherman, grew up here in the Half Moon Bay area of Pacifica. And, he plotted a pretty important curve off of just 5 data points, and as everyone knows, it's held true remarkably to this day, even though it's been recast several times into ways he never actually stated. But the sort of consensus that we have today is at least a gestalt that everyone has, that we're doubling computer power roughly every 12 to 18 months, depending on who you talk to. Now, the coolest thing about Moore's Law, and I show this graph for 2 reasons. One, because I think it's the most important graph of all technology business. And second, because every time I show it, I say that I show it in any presentation I'm giving, regardless of topic. And I always ask the question, how many people have seen Ray Kurzweil's curve of Moore's Law, which is the 100-year abstraction of Moore's Law, now 110 years. Some of you must have seen it. Don't be shy. But it's actually maybe 22% of the room. That is on average. Every talk I give, the percentage doesn't change, and I'm not sure why. So let me reemphasize why I think it's so important. What's that?
He has no units in this graph.
Well, not all of them. This one is.
Kurzweil doesn't. Kurzweil has his bogus graphs and just exponential without any.
Oh, he's got a whole book full of graphs,
Yeah.
right? Well, not so bogus. That would be a jump. I mean, that's an interesting point. So this graph has been vetted recently by the Santa Fe Institute in some degree of depth to say, instead of just drawing what I don't like is this sort of like white, squiggly, double exponential, these kind of eyeballs, I could see a straight line just as easily. But they have at least gone in and look at the data points and say, is it a power law? Is it an exponential? Is it a double exponential? Is it sublinear? It's a logarithmic scale, of course. So Kurzweil's argument is a double exponential, slightly upticking curve. SFI thinks it fits better to a power law, but in any case, it's a massive compounding curve over 110 years, for which there's probably no parallel in business, certainly not technology business, where the pace of change seems and is ever accelerating, partially because of this curve. What we're plotting here is calculations per second $1,000 can buy. Why are we doing that? Because no one buys transistors, right? There's no customer, at least in the integrated circuit world, that is. In discretes, of course, there are. People buy computation or they buy storage. That's what matters. That's what Moore's Law is all about. And by either metric, you see a similar curve over long periods of time. So this abstraction allows you across the color bands to compare different technologies, right? And what's astounding is people didn't know they were form-fitting to a curve. There are dots below the curve. This is the frontier of human capacity, the best price performance computer of the day. And the takeaways are, well, first, we use our tools to build better tools and so on and so forth, computer-controlled machines, and then better lithography equipment, better simulation tools, most importantly of late, to build better and better systems. Second major takeaway is that it spanned 5 paradigms of technology already. What might be the next one? That's been an investment thesis for us from molecular electronics and quantum computing. But I think the most important points are no one knew they were form-fitting to a curve, which is kind of interesting. It begs the almost cosmological question of why and will it continue and will it saturate. It also is completely exogenous to the economy. Right? World War I, World War II, Great Depression has had no impact on the pace of innovation. Scientists don't rest during recessions. Now, the companies behind these dots may have gone out of business like flies on a windscreen based on the economy, but they haven't changed the pace of innovation, which is astounding observation over a long period of time, and one I think should really take some time to sink in. People recently, Ryan Arthur and others have written, Kevin Kelly in his most recent book, What Technology Wants, that not only is this exogenous to the economy, it is curves like this that create the economy. And they make the argument that every idea, every innovation is the product of prior innovations, usually a pair, sometimes more. The really radical ones are interdisciplinary. And if you take that premise as possibly true, that all good ideas happen not in isolation, they occur in remarkably synchronized fashion across the planet, and they are the compounding of prior innovations, then an interesting outgrowth of that observation is that the combinatorial possibility space of idea combinations is itself growing exponentially, right? So we have understandings of electromagnetism today and the circuitry that has ensued that allows us to build things we otherwise couldn't. And there's a sequence of innovations that allows more innovation and so on and so forth. So there's at least one theory that this isn't just a weird, people form-fitting to a curve like people used to say in the early days of Moore's Law. It's like, oh, there's a whole industry roadmap and therefore everyone's purposely trying to just form-fit to, a forecast that was put out by the industry roadmap. Well, these guys didn't know there was an industry roadmap and they weren't form-fitting to anything. And also, it's the concatenation of ideas that I think is most powerful. Okay. Now, let me actually go back for just one second. And then another interesting takeaway is that this is some enormous scale change, right? As you reach certain thresholds, a formerly lab science becomes a simulation science, right? The life sciences industry is going through that revolution as we speak over the last decade, where things that were done through trial and error experimentation can be done in silico, and therefore the pace of innovation dramatically improves. What's happening of late is that there's some new thresholds in energy, clean tech markets, fuels and chemicals, even rockets and cars, where the ability to simulate something like, do I need to actually crash the car, or can I just simulate how it will crash before, and send your very first vehicle to the government for crash testing, confident it will work based on simulation. Just like Boeing designs their planes entirely in silico without the wind tunnels, computational power allows you to do things much more quickly, and it revolutionizes industry after industry. So that's why Moore's law is so important, not just to first computers, then communications and telecom and datacom, the obvious ones, right? But life sciences, vehicle design, fuels and chemicals, and now biology. Just one random example, again, gratuitous opportunity to show both one of my favorite activities. I was launching rockets on Sunday, but also a company we invested in that's used Moore's law in a variety of different ways to redesign how rockets are built at roughly, a tenth the cost of incumbents, where they use the same electronics chassis throughout, the same FPGA module for all control elements, and just all kinds of new ways. The way you'd build a rocket today, not the way you'd build it 23 years ago or so, when Atlas and Delta were coming together. And allowed them on their Falcon 9 launch to succeed, get into orbit on the first attempt. A lot of simulation went into that, whereas the last attempt to build a new rocket in the United States, the Atlas, took 13 crashes in a row, 13 explosions and dramatic failures before they finally put something in orbit, thanks to Moore's law. Now, for a historic throwback machine, back to the 90s and then into early 2000s, if you look at the internet, I'm preaching to the choir here about how important that is and how it accelerates technology's proliferation itself, right? So if you had Moore's law as a phenomenon, the rate at which humans are networking is itself increasing the pace of change. If you think about pockets of ideas, how many good entrepreneurs on the planet can have their ideas see the light of day? That's dramatically changing. Here we're compensating for, if all these companies had launched at the same date, which they didn't. Really interesting how their pace of growth, earlier the buddy communication systems, ICQ out of Israel, Hotmail, actually, does anyone know where Hotmail is based? Pretty close. They purposely chose Fremont. They did move later, so there was a later location that was closer. They really put a lot of marketing thought into this. We're going to be in Fremont on Liberty Avenue and launched on the 4th of July, free email. And of course, they got no press because they launched on the 4th of July. No one's working on the 4th of July. But in prior talks, people usually think India. And of course, these companies could have been anywhere. Skype was built in Estonia by 4 programmers in 4 months. Hotmail by 2 programmers in 3 months. And those companies could be and are increasingly anywhere today. Wow, it is based in Serbia. You can build and launch a product. It's an obvious point. But also the pace at which products can proliferate globally is unprecedented. At the time, these were record setters for the rate at which a new product had been subscribed to by users over time. And of course, now, as you know, Skype, 400 million users, almost like the 3rd largest telco in the world, and growing great guns still today. So this globalization effect is important, and it further accelerates the proliferation of ideas. And if you think about ideas mating, ideas having sex, the way Matt Ridley would describe it, as the source of innovation, that's what makes Silicon Valley so magical. The rate at which interdisciplinary ideas and intergeographically sort of dispersed ideas can cross-pollinate is a powerful driver of the pace of innovation. There's a loose analogy one could draw to differential immunity, like when the missionaries first came to the New World and killed everyone through the transmission of smallpox and related diseases. Ideas are the same way. If disruption is good, remember, if change is good, like killing off all the incumbents is a good thing in your mind, then the extent to which ideas can cross-pollinate across academic disciplines that had been perhaps segregated from each other like islands through their vernacular and systems theory, and then finally come back together around some new locus of conversation like nanotech or synthetic biology, where the folks who weren't talking to each other now start to talk to each other, usually at universities. That's where you see a proliferation of radical ideas. An example recently of how that spills into energy markets, now trillion-dollar industries, water purification, solid-state lighting, energy and clean tech and fuels and chemicals are all markets that are 10 to 100 times bigger than anything the venture community has ever aspired to attack, if you will. An example just from our portfolio, Enternoc, which went public a few years back, it looks a lot like an internet company under the covers. What they do is they stitch together demand sort of shedding opportunities and demand generation opportunities at industrial accounts. So imagine a hospital, a Safeway store, what have you. They have, some cases, diesel gensets for backup power, and they have the ability to shed load, like tune down the lighting, lower the temperature on the fridge for hour at a time, let's say. And by stitching all those industrial accounts together, they can present virtual load shedding to a utility and say, look, instead of having a brownout, or instead of having to build this natural gas peaking power plant that you only turn on a few hours each year for those peak load moments, instead, let's use our information network to turn on diesel gensets, worst case, or just shed load in your region on demand. And in exchange for that option value, the option to do it whenever the utility wants, they get a constant, steady source of money every month that they then share with these industrial partners. So it's a network effect. It's an internet company. It's only made possible by the ubiquitous data networks that span across these industrial accounts. And so it grows like an internet company, right? They got to profitability on $3 million of invested capital, which is, again, contrary to what people might think for energy clean tech markets. It's places like that where we're most excited, where it feels like information technology, and it is, business applied to trillion-dollar markets. And by the way, they've already prevented the manufacture of 70 gas-fired plants on the East Coast of the United States alone through their virtual network. I'm not going to spend any time on this. In some context, people are really interested about energy clean tech. I can come back to it in Q&A if you want. But we've been investing and are probably the most active investor globally in energy and clean tech products. This is about a couple months old, but there are about 75 companies across the network, about 45 from this office here alone. We started in energy generation, distribution, and storage kinds of plays. We're much more interested in the ones on the right side of the page at this time, which is more efficient use around solid-state lighting, building materials, what have you, fuels and chemicals around synthetic biology, and resource management, a broad catch-all for everything from agriculture to water purification and things like that. Just for a sense that there are real businesses here, the revenues have been doubling about every year for this aggregate portfolio, and this group alone, I think, will do about $1.4 billion in revenue this year, up 100% from last year. Now, what's one example that's kind of interesting and sexy? I love Tesla, and I'm biased, of course. But I put together a couple of slides for a Castrol management retreat. It blew my mind. This is a company that has $10 billion a year in sales, and the only product they make is lubricants for internal combustion engines. Right, that's imagine having a $10 billion industry. It's like the buggy whip, supplier of the last century, and they're gleefully, that's all they do. They have no intent to go outside of that. And I had to tell them that entire industry is going away. There will be no internal combustion engine, right, in some near-term future, like 50 to 75 years from now. And they were aghast. And one of the reasons is, just for those who don't know, these, if it were a gas engine, it's about one of the least efficient things on the planet. It wastes 80% of its energy in heat that is not used for anything useful. And only 0.3% of the fuel you burn in your car, if you're driving a gas car, moves you, the passenger. 0.3%. I believe all transportation will be electric. Airplanes is a much longer debate, and it'll take the longest time. But planes, trains, automobiles, the new ones are already. They use diesel gen sets inline to run the motors. It's just a better way to build every vehicle you could imagine. Even if you generate electricity by burning oil, which you wouldn't, of course, eventually it'd be all fusion and fission. But even if you use stupid ways, like one big centralized oil burning, fossil fuel burning machine, it's still better to transmit that power, go through the battery inefficiencies, and run an electric motor. In a car, for sure. In a train, if you have better storage. The problem with trains today and tanks and heavy equipment is they use electric motors, but they don't have good storage density. How can we store enough energy on the vehicle to make that make sense? So in a long-winded way, what I want to talk about transportation is it itself is an enormous industry ripe for change, and all kinds of information economies are going to percolate through the vehicle. It's going to be the mobile iPad, if you will. Oh, let me go back one. But that's the high end. When we talk about disruptive change, it's pretty interesting. Clayton Christian talks about this pincher move, and the auto industry is an easy example everyone I think can understand, is that you got this high-end, fancy brand, luxury kind of segment, if you will, that the mainstream auto companies can try to ignore and say, well, that's just going to be, as with past luxury cars, a high-end niche, a Ferrari, a Lamborghini kind of category that doesn't matter to us, right? And Tesla would disagree, but that's one way to dismiss the new entrant. The other category that can be dismissed is the low end, the products that are just useless to your current customer base. So if you're selling, Hummers or F-150 pickup trucks, there are certain categories of vehicles you're just not watching with a lot of detail. And the example I love to give is China today has 120 million electric vehicles buzzing around its roads. Think about that for a second. 120 million electric vehicles sold by 1,300 different Chinese manufacturers. Today. That's not the future. I gave a sneak peek, unfortunately, before, so you didn't have the time to think about what the hell I'm talking about. It's these two-wheelers, right? They're the equivalent of electric Vespas, e-bikes, and scooters. What's astounding is the pace at which they've taken off in China. And just as an example, let me show you that graph. And I've updated it. This was some work initially done by Jonathan Weinert out of Chevron, and I've been gathering the last few years of data just to update his curve, because ever since he joined Chevron, he isn't really supposed to be focusing on this so much. Electric two-wheelers is the green curve. It's the most popular powered vehicle category in China today, and has been for a while. Now, what's interesting is what made this change occur. There's been a few things. First, there was policy, right? It's amazing when you have a government run by engineers, they actually set policy, in a slightly different way than other democracies around the world. So they just say, hey, we're going to outlaw these two-cycle, polluting bikes from our cities. Eventually, we got up to 150 cities banned petroleum two-wheelers. Then they start to get scrapped. 53,000 of them are scrapped in Shanghai. Then they give a law granting them the right to the bike lanes. So kind of like commute lane policy here. Not you can see how it's correlating with growth. And by the way, technology improved, right? They switched to VRLA batteries. They got a 30% improvement in yield and efficiency there. They switched to brushless motors in the early days. That got them also about a 30% efficiency gain. So there was technology improvement as well in the background. And oh, by the way, purchasing power of the average person in China, doubled roughly during this period. So that also helps. Then there's some other changes. Now, here's an interesting question. What do you think was the biggest kicker and sort of what this knee in the curve? What was the biggest driver, at least in Jonathan's mind, of this transition? Does anyone want to venture a guess? Nothing to do with policy. It was nothing intentional. It was SARS. People didn't want to ride on the bus. And then they bought these electric two-wheelers as a substitute for bus transport. And when they actually paid for them, they realized it cost less than riding the bus. If you do an all-in cost analysis, the E2W, it's actually cheaper to buy and operate one of these for solo passenger use than to ride the buses in China. And that, by the way, was perceived to be even lower still because that factors in battery replacement over its life, which most people, when they first buy it, they don't realize they're going to have to replace those crappy batteries that they use over there, the VRLA batteries, about every year and a half to 2 years. But even when you factor it all in and actually do a real cost economics, it's cheaper, which is kind of interesting. Those 1,300 different vendors in the top right corner are examples of their latest products. The 4 largest manufacturers are now doing four-wheelers. These cars sell for between $2,000 and $4,000. A lot of them, to the criticism of the government, are not even regulated as cars. They're just selling them with absolutely no nod to the crash safety laws of the country. But nevertheless, that's the bottom end, right? That's a great example of Craig Christensen's coming from the bottom. By the time they've shipped more units than anyone else, it'll be a bit too late for other auto companies. Now, by the way, looking back in time 100 years, you look at cumulative electricity use in the U.S., right? In 1900, transportation was the single largest consumptive source of electricity in the U.S., and I believe it will become something closer to that again in the future, sort of just for the long view. Okay, that was just a brief digression on something that I think is pretty interesting, but not the main point. The main point of that, as an example, was disruptive change is occurring in industries that had been sheltered from disruptive change for a while, right? When Tesla went public, it was the first U.S. car company to go public since Henry Ford. So it has been sheltered for a while, just as I would argue fuels and chemicals have been as well, and other huge industries. So now accelerating change, things like Moore's law. And here's where Sebastian's good point about Kurzweil's curves being this just fire hose of how shall I put it, fire hose of bias perspectives. Nevertheless, if you look at some of the examples where the curves hold really well, and let's say other people did the analysis, if you just want to look at it that way, there's, of course, IT-related topics where you see similar curves. IBM's done analysis of the disk drive industry, or mass storage, if you will, and it holds even more powerfully than Moore's law over a slightly shorter period of time, but more dramatic slope of change. Obviously, networking, all kinds of different metrics of the size and scope of the internet. But also biological themes. Evolution itself, over hundreds of millions of years, follows a very similar accelerating pace of change, which is fascinating. And we are now, of course, really, you think about how does that accelerate in our lifetimes? How do we feel accelerating change in technologies? Of course, the vector of abstraction is moving to our technologies, not our biological systems. So you take that broader definition of us and our technological substrates, meaning our societal memes and norms, the technologies we build and in the world that we live in, our extended self, that is evolving at an accelerating pace of change, even in the current day. But also a lot of sort of life science-like things, like in that curve there, that's Dickerson's law. Not a very famous guy, but it's even more predictive than Moore's law itself. It's held to 0.5% accuracy to the current day over 35 years when he first said it, of how many proteins are going to crystallize each year. And in the 1965, he predicted a number that's held true to today. At least a formula, that is. And the number is a genes mapped. I think genes mapped is an interesting proxy for the information accrual and accumulation in life sciences. And so I'll give you an example of that. On the left, you have the Human Genome Project. How many genes have been checked into the gene bank, the public, effort? And this exponential curve looks familiar to some now. At the time, it was deeply contentious, especially midway, when very little progress had been made, and naysayers were saying, "Hey, the shotgun sequencing approach will never work." And Craig Venter and the team realized, "Hey, you guys think it's going to take this long? We can look forward to the computers that will be available 4 years from now." And we don't really need to work so hard in the early days because we don't really want to use the computers in the early days. Let's just collect samples and do all the shotgun sequencing at the back end and do half the project in the last 6 months. And that's exactly how it played out. The pace of Moore's law drove the shotgun sequencing technology. Basically, computers have to reassemble the genetic code from the nebulized random fragments that are overlapping. And sure enough, it kicked into gear just there. Now, what's intriguing is that scientists didn't like rest on their laurels and sort of stop and digest as one might have assumed. And in fact, there's some criticism that human health hasn't improved much from this research. They moved on to microbes. And what's astounding is if you look on the right curve, this whole human genome project is that little part of the curve. And since then, it has just mushroomed like crazy. Now, what's interesting is you might say, well, is it, surely that's some sort of local peak. But what's even more astounding, because this doesn't take us to the current day, is that if you look in the last 18 months, one team, again, Craig Venner, sailing around the world, shotgun sequencing whole ecosystems now at a time. Again, using Moore's law to say, hey, now the computers are good enough that we don't even care to segregate the tens of millions of organisms that are in one little milliliter of seawater that we sample, the bacteria and viruses. We're just going to put the whole damn ecosystem unsegregated through our methodology and deduce all the interesting genes that matter out there. Right? Well, that team alone has grown this data set tenfold. Right? So this now is 10% of known genes on the planet today. The number of known genes for energy transduction, how do we harvest energy from the sun, have grown 100-fold. Things like chlorophyll, the rhodopsins, the things that have evolved in the ocean water over longer periods of time and are more efficient than land-based plants and animals. Fascinating stuff, right? Problem is, why would you ever done this? Because in biotech 1.0, if you don't have the host organism from which to physically cut and paste the genes, what good is the data, right? And so people may not have thought to do this 10 years ago because it would have just been an academic exercise at best. Here's a bunch of genes, but we don't know what to do with it. It could have been like, maybe a statistical study, but nothing actionable. No business could have come out of that. Well, what's changed and what Craig Venner saw was another exponential curve. These ones, by the way, done by Carlson, don't even worry about the axis at this point because what matters is the relative slopes. Red is Moore's law. Blue is the advances that have been made in gene sequencing, which is reading the code of life. And green is the pace of change in the synthesis of genes, writing the code of life. And slight differences in slope have a dramatic compounding impact over time. So if you put this on a linear graph, gene synthesis technology advances would make Moore's law look flatline in comparison, for example. Now, what are we referring to here? We're literally talking about emailing files to different places around the planet. Give me an A, give me a T, give me a GGC, whatever, and then getting a FedEx back of that oligonucleotide. Sometimes several series of these. And they're all over the place. This is a local company just down the street, DNA 2.0. They literally have beakers affectionately labeled A, T, G, and C, and the things are just printing them out. There's no animals are involved, right? This is just, or chemistry in the lab. Well, the ability to predict that falling cost of gene synthesis allowed people to think about, when will we build the first virus? 2002. Sure enough, it happened. When will we build the first free-living organism that can propagate? The first organism whose parents are a computer, in the sense that it's just code pulled out of the air with embedded URLs in its code and all kinds of interesting poems and quotes, built base pair by base pair from the ground up with no animals involved. When would that happen? Just a few months ago. Company on the right-hand side, Synthetic Genomics, again led by Craig Venner, did that. It's an astounding accomplishment. First, that you can take 100% of the DNA out of an organism, put it in an entirely foreign bolus, and have it change species, change phenotype from one to another. And they showed that across organisms that were as genetically different as mice and men, just for symbolic value, which actually means pretty darn close. It turns out. But these are single-cell organisms, don't get me wrong. No one has taken on mammalian cells. They're quite a bit larger and more complex. But it's a profound, I think, watershed achievement in a field that won't have business applications this year because directly, it will indirectly, but not directly. We're not going to build new life forms, don't get me wrong. But that's where we're heading in the conversation. What we will do is high throughput experimentation at a pace that hasn't been done before. It'll radically change the process of innovation, where you don't have to find the host organism to test a hypothesis. Well, what if we spliced in this version of a rhodopsin that has a different frequency tuning ability to a different spectra of light? You can run, as George Church at Harvard has shown, using a different methodology, 4 billion experiments a day of genetically different organisms. It's just mind-blowingly different. Biotech 2.0 is mind-blowingly different than Biotech 1.0 in both the pace of innovation and the rate at which we can run experiments. It will, as this is all a big lead up to say, well, it begs the question what one would design, but the capacity to design is with us now. And by the way, when teenagers are playing with it, then it's somehow hit mainstream. So for those familiar with the International Genetically Engineered Machines Competition, IGEM, started by Drew Andy, now at Stanford, formerly at MIT. Teenagers and people in their early 20s are, re-engineering E. coli like it was Lego bricks, right? Make it into an oscillating repeater with logic gates, build it in a chemical sensor, just, to drag and drop like a Mindstorm's NXT kind of workspace and make organisms that do fascinating things, right? There was a binary system where one organism was a sensor, the other was a therapeutic for Crohn's disease. It's not yet in animal trials, but at least on paper it seems quite plausible that it could work. Another team has done, they've re-engineered the E. coli to smell better because they smell like that from which they come, and they just didn't want to work with something that smelled like that all day, so they made it smell like bananas. And then a third team created a biofilm and had it change its kind of like the e-ink screens on a Kindle, change the way in which it portrays a color based on light exposure. So it's literally like a film that you can expose to light with higher resolution than normal film, and what I would call e-Polaroid. And that I think should at least be played with some more. It's a fun one. So in other words, you just take these little paper blotters at the low end, and they're just playing around with this stuff, splicing it together. They even have their own comic book. Oh well, I accidentally left that slide in. Well, what is the business application in the near term, not the immediate term, but the next few years, maybe a decade out, is 90% of all organic chemicals. In fact, everything you can see and touch in this room, not the underlying metals, but the surface coatings, just about everything in this room probably came from petroleum or natural gas, which is pretty astounding because we have organic coatings on everything. I mean, this entire thing, for example. And inevitably, it'll be known as the formerly petrochemical industry. Because I think we'll look back at some point in the distant future, maybe 50 years, to the present day and marvel that we had this incredibly rich resource on the planet, all burned it. Right? It's the least creative thing you could do with a resource like that. You think of it as like the Amazon basin. Well, there's a lot of things you do with the Amazon basin. Burning it is the least creative of those things. Instead, you could bioconvert it into all kinds of fuels and chemicals that have more rich use, that aren't just burned. I should say not fuels and chemicals, but chemicals. And so these organisms can assemble things with with a precision in their stereochemistry that is very valuable. Is it the left-handed or right-handed version of the molecule? Is it the sugar that's undigestible or digestible? They can do that without a statistical sample, but as a metabolic pathway, just creating one, not the other. So there's some big companies that have woken up to this. So ExxonMobil has probably spent more in marketing than science, but they have put $600 million towards the science with synthetic genomics. And there's a bunch of other companies working on, in this case, for example, re-engineering algae to continuously secrete their oils across the cell membrane. So unlike a sort of farming approach where you have to grow, kill, extract the oils to make biofuels or fish foods or any number of other lipids, you have continuous secretion and a very inexpensive separation process where they just kind of continuously get separated off and the organism makes more and more and more. That could be revolutionary to algae-based fuels and chemicals. And there's other really interesting projects like converting coal to natural gas underground, which is already done biogenically. 10% of our natural gas comes from there. There's been some recent efforts that have shown you get 100 to maybe 1,000-fold improvement in that, where you take the dirtiest burning of the fossil fuels, coal with all its sulfur and mercury, leave it in the ground, convert it to natural gas, which is the cleanest burning, right? You burn it in your kitchen without a fume hood, and without any, in a sense, energy infusion. You don't actually have to crack or frack the wells. You just let the microbes do the work. And when they did genetic sampling of those wells, it was kind of amazing. They drilled down, pulled up a genetic time capsule of sorts. The organisms living in there had a whole rich ecosystem, completely isolated from all sources of light or contact with the outside world. They were stripping stripping electrons off the carbon bonds. There were spirochetes that were living on these things. The whole little time capsule that had been segregated from the rest of the world for 70 million years. And fascinating. Everywhere you look on the planet, you find life doing very interesting stuff. What does all that mean? Well, there's an increasing sense that this world we live in, at least of late, is completely unpredictable. Financial crises and collapses, which, by the way, is good for startups too. I forgot to mention sources of disruption. A good financial collapse helps new entrants more than it hurts them, and it hurts incumbents and their debt-laden balance sheets and union contracts and pension contracts more than it hurts a startup. So if you're in the automotive industry, what better time to compete with GM and Toyota? Right? Just think about it from the startup's point of view. Anyway, black swan events could be considered good or bad depending on your point of view, but there are things that make sense in retrospect, like Google being successful. Of course, we all understand why Google is successful, but when they launched, I'm not sure any of the investors, at least, to make fun of our brethren, could have told you here's how it's going to play out. Here's the roadmap of how Google will succeed. It's what, in retrospect, someone like Nicholas Taleb would call a black swan event. Those aren't going away. Right? Financial crises, near collapses of financial systems, the pace at which those events occur is going to accelerate, and it's going to increasingly define our world. You can do retrospective analysis of the stock market and say it's only those huge intraday swings that seem like outliers that really drive change over time. If you took those out, the stock market doesn't look anything like it really does today, and increasingly will be so. Well, you might ask yourself, that's kind of weird. And how do I plan around that? And as venture firms, we think about that too, and we try to do portfolios, and we try to only be equity investors, not debt lenders, because you can take advantage of upside, and you have limited downside. You can only lose 100% of your money in any one company, unlike some other kinds of synthetic vehicles. But you might also ask the question, well, is there something completely out of left field that could change computing? Is that kind of stable? Because processors, the way we kind of know them, parallel processing, not that radically different, but is computing more or less a stable thing? Well, some of you may have caught the Google announcement with Harmit and Evan earlier in the year of the use of a quantum computer from Vancouver to work on some machine learning tasks around Google goggles and the recognition of cars in a particular demo study. And they found both through, in the way in which they did discrete machine learning versus continuous variables and the way in which they use a quantum computer versus a classical computer, they got improvements over the way machine learning is done today. And my guess is almost everyone here has some interaction with machine learning algorithms. What's fascinating about quantum computers is, for those familiar with them, they're just completely different ways of computing. The only physics explanation for how they work is the engagement of parallel universes, just to get a sense of how different it is. And the sort of the diffraction patterns that occur across nearly neighboring parallel universes. And I'm not joking. That is literally the only explanation that actually matches with measured reality. And David Deutsch from Oxford is one of the few professors are willing to just go on a limb and say that. I mean, guys, you gotta admit it. This is what the two-slit experiment and everything else in physics points to. But what's even more interesting is the certain classes of problems, things that you can map to a graph. This is an application-specific quantum processor in this particular case. Problems like the traveling salesman problem, Monte Carlo simulations. It turns out molecular modeling, optimization algorithms of almost every type can be mapped onto this quite efficiently, but not all computation can. So certain classes of really hairy problems, like FedEx route optimization. If you look at that class of problems, the ones that people really care about, that are at the cutting edge of what we can do computationally today in a high-end data center, and all machine learning, for example. If the pace of progress in quantum computing follows what I've come to call Rose's law, because Geordie Rose, the founder of this company, has sort of plotted the points and made a claim early on when I first met him that every year we're going to do twice as many qubits as the prior year. By the way, every time you add a qubit, you almost double the power of the computer. It's not like the Moore's law thing about adding a bit doesn't, well, like from a memory register size it does, but not from a computational power. Here it really does correlate with computational power, doubling with each qubit. And we've been doubling the number of qubits each year, right? So if that pace of progress continues, and that curve's held for 7 years now. And remember, Gordon Moore had 5 data points. So we got 7 data points versus 5. If that curve continues for the next 7 years, and I really have no reason to believe why it would or wouldn't, because it's this, semiconductor process. It's pretty linear tiling. We're not talking about changing the design as you scale. It's just putting more of these next to each other. So if this trend continues for the next 7 years as the prior 7, one of these computers that would fit roughly in the space of this podium area could outperform all computers on the planet combined, all computers ever made. Then you give it a few more spins, and soon it's outperforming all computers that ever could be made with any traditional architecture, even if you used all the matter in the universe to build them and gave the entire length of the universe as a compute time. They still wouldn't solve the problems. Now, obviously, we get around those. We use heuristics, right? We're talking about the brute force solving of problems versus using heuristic, where we've long since given up on solving the problem. NP complete problems, things that, or NP hard problems rather. So that's pretty interesting. It begs some interesting questions. Okay, let me finish up soon here. Good. I think I'm right on time. So this is the last topic. Now, I think a lot of folks here, in some ways, I shouldn't say that. I don't know if you dream of building complex systems. I sure do. As I think about the big unsolved problems in science, especially information science, what are the ones where at least some people say that will never be done? And I always love that as a challenge. Either that's impossible or we'll never do that. Like artificial intelligence that exceeds human intelligence, or nanorobots doing amazing things. That's actually probably the hardest of all of them. Or designing microbes from scratch that do our bidding, right? In the synthetic biology side, we can build them now, but what's the code? We don't have the programming environment, if you will, or understanding of the interpreters and compilers of that world. Well, all these have something in common. They are in many ways the attempt to build a complex system. And now we're building, no single human understands Windows, right? And we're trying to build things in many areas and many artifacts in our world that are beyond human understanding, meaning any one human. So we have teams of humans that are sort of at that frontier of human understanding in the paradigm I designed, but we're hitting some limits in certain areas. So I first put this slide together in 2001 or 2002. Around nanotech. So there was a lot of nanotech specific vernacular. I pulled it out because I realized the big labels kind of apply to all these areas. But imagine we were first thinking about, dreams of nanotech futures, these little nanorobots that do amazing stuff. How would we get there from here, right? Because as an investor, we always have to think about, we can't invest in a dream that just says, let's just hunker down for 20 years and something pops out amazingly at the other end of it. That's a bad investment thesis. But is there a way to engage with markets, customers, and iteratively get to some vision, some sort of shining star that motivates the team to work hard? And there have been two approaches we could think of paradigms for how you get there. And this applies to all kinds of stuff. This applies to architecture, art. There's a whole bunch of domains of activity for which you could talk about a top-down or bottom-up. But specifically what I mean by this is top-down is sort of the engineering approach to things. The Germanic, if you will, tradition of take the semiconductor industry. We will build tools to scale down from above. We will inherit interfaces of scale from above, meaning things that are big in discrete capacitors, printed circuit boards, plugs that go in walls, the big stuff. We couple down to smaller and smaller things with technologies where the frontier is sort of that think about that red point coming down, working on that frontier. We're not reinventing the plug as much. We're sort of working on the cutting edge of gate oxides or whatever might be down to the nanoscale today. And the pace of change is slow, incremental, and generates revenue along the way, right? Every Intel processor has a market, right? They didn't hunker down for 20 years and then come out with some new architecture at the other end of it. And so it's slow and steady. That's why HP, IBM, and everyone doing research in nanotech said all of our interesting products will be 20 years out. It made sense. It probably will be. But there was this other group, Kevin Kelly wrote about it and others, that really inspired me, which were doing radical things in the near term, like Angela Belcher's early work re-engineering viruses to do lithography, and it was fascinating work. A little bit different, though. Grown, iterated, a little bit out of control. Movies have been written with that. Very powerful, but lacking a lot of system theory. How do you really dictate the outcome of this? And it's an area of active research in evolution design and things of the sort. But most interestingly, at least here was an existence proof of transcendence, where if you think about evolutionary algorithms, they are capable of producing products that are more complex than their antecedents. And what I mean by their antecedents are people like us if we're putting it together, the components of biological evolution looking back in time. Now, there is one asterisk to put on that. Some deep in this theory argue that, in fact, evolutionary algorithms don't produce anything more complex than their selection pressure. And how you design the selection pressure, which organism survives, which gets killed off, is actually the embodiment of the magic. And it, in our real world, where we co-evolve with all our artifacts, is remarkably complex. It's the matrix, if you will, that we live in. And in a rarefied laboratory environment, usually simplify it dramatically. Say, I'm just going to select for the fastest bubble sort algorithm. No, it's not even bubble sort, the fastest sorting algorithm, and just kind of genetically mutate sort algorithms and eventually pick the fastest one. Well, that's a very simple selection mechanism, and you generate a sorting algorithm. And what's subtle in that argument is, is there still as much power as I'm about to describe? That's sort of the asterisk that I want to put there, because that's something I don't fully understand myself, but I find fascinating. So let me give an example. Let's imagine we think about building AI, because I would hope everyone here would think that's interesting if it could be done, and may at some point in their life have debated with somebody whether it can be done. One of my favorite books on intelligence by Jeff Hawkins, I think I agree with everything I read in the book about how the cortex works and how we're going to build intelligent machines in the future, except for his comments on page 219, which you don't actually have to read them. I'll just summarize them as, he believes that once we build iteratively, right, not like rules-based systems or traditional AI and back from the 60s, but when we grow an artificial intelligence, that we'll somehow be able to magically cut and paste things like English and French speaking capabilities as if they were modules, or down here, sell and swap memory configurations to reprogram intelligent machines to do entirely new things as if you're just installing new software. At some level, he's right. Yes, it could just be software running on a computer. That's true, and that's powerful and worth thinking about. But I think the profound, in my opinion, error in that analysis that conflates the power of design and the power of evolution is that we would know how to do this in any way without expending perhaps more effort than it took to build the system in reverse engineering it. So take, for example, you grow a neural network to do speech recognition. To actually decipher how is that speech recognition algorithm, the resulting algorithm working, what are the mechanisms that work, takes a lot, does not come out, right? The decomposition of design is not free. Similarly, you think about how long it's taken to do reverse engineer the human brain, which is itself, of course, a product of iterative algorithms of evolution and organic growth and pruning based on usage-based feedback. Understanding the brain and its subcomponents is remarkably difficult, right? If we could very quickly run experiments, billions of experiments per day, per second, and could grow an artificial intelligence, if we could do that, it would be just as difficult to reverse engineer as the human brain today, if not more so, because it would have started with a foreign substrate and its interfaces would be kind of alien to us. So I don't think there's any reason why us poor little humans, in terms of our cognitive capacities and lack of theory for this, could in any way take a really complex system and just say, oh yes, here's the decomposition of design, because there's no design. The decomposition of subsystems, starting to do that. Think about how many human minds are currently trying to understand our own brains. So What is it about these evolved systems that makes them so inscrutable? Well, you get these emergent layers of abstraction. That helps, which is, in human evolution, right, you don't tinker with basic genetic code when we went from primates to humans, right? We don't tinker with amino acids or protein signaling. We don't really tinker with much of the hierarchy of evolutionary historical artifacts. It's all in the network. It's all in the number of nodes in our brain, right? And that's really fundamental. It wasn't even a new cell or a new neuron. Some might argue the mirror neuron, but it's really how it's wired, not so much that novel a concept as the neuron itself. And that's a new vector of indirection. I would argue that evolution today is far outpaced by anything in the biological world, and it's all technological. We'll get to that later. Now, the subsystem inscrutability. For anyone who's worked in these areas, it sort of comes part and parcel, and it's obvious. But when Danny Hillis, for example, did genetic programming to build a better sort algorithm and to compete with bubble sort, it did a pretty good job at sorting. It didn't beat the best human design. That's a pretty simple task. Design does fairly well at it. But it did better than most programmers can program. So this completely artificial evolution process beat most computer scientists in their attempt to write from scratch the best sort algorithm they could write. But it made absolutely no sense. The code was full of it was a very large code base. It had all kinds of crazy stuff in it that made absolutely no sense, and he never actually got around to figuring out how it works. Same is true with neural networks, an area I did some research in. It's when I first sensitized me to the fact that it's the process that you learn about, not the product. Right? When you do run another experiment, or let's try that one again, you can tweak mutation rate, tweak selection pressure, tweak whatever, parameters of communication, if you will, in the growing system. But you don't say, oh, okay, here's the output, here's what makes sense, let's take what we've built and build more on it. You really can't do that. So the learning is at the process, not the system level, and it's a black box defined by its interfaces. What really is understandable, think about the brain, is the interfaces, the sensory cortex, right? We can hack in from the outside. When there's something like the retina, there's an interface to the world we know. So most of the brain studies have come in through the auditory cortex, the sensory, the visual system, and that makes a lot more sense than the core cortex itself. And maybe why is this? And I'll be curious maybe in Q&A if anyone has an argument against this, because I find it fascinating, is that there's no mathematical shortcut. There's no way to take an iterative algorithm like a fractal or Rule 31 in a cellular automata or evolution itself and say, given the output of that process, run the tape backwards and tell me how we got there, having only the output as your input, right? In other words, only with the artifact of creation, with an evolved human. Show me how evolution got us here, right? There's no word reverse evolve like there is reverse engineer, right? And our intuition does not lend itself well to figuring out that process because information is lost at each step along the way. From a Wolfram sense of computational equivalence, you could argue that this will never be found and that there is no mathematical shortcut in that sort of the logical depth, if you will, of complexity in an emergent system is really where all the action is. So, what is this dichotomy of design I'm talking about? Again, and just to jump to the chase so I don't mislead people, I think the richness is to explore where this dichotomy doesn't hold, to not believe that there has to be this breakpoint. So I'm first going to describe it as a diverging path of the futures, where let's say two different research teams working on AI are going to have very little to say with each other if one's going the design route and the other's going the evolved route. But I want to argue that hopefully someone can figure out a way to break that dichotomy. So when you design something, you have control generally. What you build is very brittle, just think of Windows, versus things that are evolved. And they can transcend in terms of complexity what their antecedents, or at least creators, if you will. You can create a process to create complexity more easily than you create the complexity itself. Here, not to denigrate all of computer science, but generally simple problems compared to really complex problems. And just for a sense of the code density difference, if you take the human genome, burn it on a CD, even without any sophisticated compression algorithm, just kind of brute force Huffman coding, it's much smaller than Microsoft Office. It just says a lot about the different methodologies of code representation, and of course the value and power of the interpreter in the case of the human genome. Subsystem clarity. Not always, but usually when you design something, if you're good about commenting your code, but even if you're not good at commenting your code, people can usually figure out, other humans can figure out what you're up to. Most of the time. Unless you're really trying to obfuscate what you're doing. And that allows for portability, modular reuse, object-oriented programming. Everything comes out of this, right? The whole field of computer science focuses on making that more efficient, right, in a compartmentalized way. Or much of computer science. I shouldn't make such sweeping generalizations. But it is in drastic contrast to the hierarchical subsystem architecture of, let's say, Rodney Brooks, the way he builds robotic control systems. I don't know if I'm going to mention this now, but if you think about the AI example, there's potentially a lot of path dependence. Some would argue you can't build an AI unless you build a physical robot that it's instantiated in. That sort of the brain in the box would never work. You'd have all kinds of weird, non-recognizable intelligences emerging. And that's a whole other interesting side debate. But Rodney, I believe, would agree with that. And how you go is very interesting. If you do a series of iterative selection pressures, does inevitably, when you're talking about intelligence, do you build in a survival instinct? Right? If only those organisms that survive some selection pressure are selected for, regardless of your attempt to evolve for friendliness or evolve for sacrificial iRobot-like rule codes, it may be an inevitable outcome that any evolutionary algorithm creates a survival instinct, which is kind of interesting. And also, this co-evolutionary islands. Back to the point of not being able to transcend the complexities of your selection pressure. If you evolve anything in a restricted environment, it will only work and be robust, resilient, and adaptive in that environment. The moment you take it out of that environment, it could be just completely slaughtered. I'll give you a great example. There's this group in the Midwest that was evolving FPGAs to do some interesting task. I forget what it was, some computational task. These are digital circuits with an SRAM bank and some gates, but they're just you can put code in, and the code reprograms the wiring and the function of the circuit. So think about it as circuit design, reduce the code in FPGAs. And they had banks and banks of these, and they're running this set of genetic algorithms and selecting for the best ones. And then they found one that just blew the doors off it. In fact, solved the problem at hand better than was any human design, better than was theoretically possible for that chip. And they're like, oh my God, this is unbelievable. The breakthrough has occurred. And they took it somewhere else and it stopped working. And they're like, oh yeah, it's not robust outside of its environment. Maybe temperature was off or vibration in the floor, who knows what, right? Okay, so it didn't work when we moved it. Let's take it back, put it back where it was. Okay, it starts working again. What is going on? It had found a way to RF couple to neighboring cells and engage their computational resources in a completely undocumented manner. Life will find a way from Jurassic Park comes to mind. So what are some of the implications of this? Well, I don't think Jeff Hawkins' thing about cut and paste is easy. I don't think Ray Kurzweil's idea that you upload your consciousness to silicon is so easy. Take phantom limb pain, right? A lot of amputees, a large percentage of them have this horrible ringing effect given neuroplasticity where they have this excruciating pain in the missing limb area even though the limb is not there, and they just want to scratch at something that's not there. Those kinds of effects at the interfaces, right? We say, well, we've got the brain in the box, but that brain in the box may be ringing horribly with its sensory system, again, unless we really understand how sensory cortex works. That's just an AI kind of geeky point. The most important point, I think, is the second one. That in all this, maybe it's obvious, but you don't learn about what you're building. You learn about the process of building it, which I think is important. And it'll have some implications on management as well. This co-evolutionary islands thing, I won't get into that so much, but the differential immunity concept carries across here too. If you evolve something in a lab, it's just not going to be ready for the real world. And does beg the question, do we need to have these technologies robustly amongst us from day one for them to ever become intelligent in a way that we would understand? And then one maybe last funny anecdote on this slide, which is if you think about the uploading folks, there's only a small handful, I think, there's a handful of people who believe that we will, through better and better brain scans and non-destructive methods of reading neuronal states, everything from every ion channel state. I mean, it's massive complexity, it's mind-boggling, but they're like, hey, follow the curves. Well, one day we'll be able to do this. Why couldn't you reinstantiate that on a silicon simulator? And an interesting thought experiment in terms of race conditions to AI futures are, given FDA regulations, if nothing else, what would you upload first? A primate, right? Do a test, see if this works before you, especially if there was a destructive upload as a thought experiment. Brad Templeton has pointed out, make sure you do bonobos, not chimps. By the way, bonobos, for those who don't know, are these incredibly cool animals that aren't really seen in zoos much because they do it in the missionary position and kids freak out, and they're basically bisexual sisterhoods of hedonists. They just do everything that you could imagine you'd see in a porn flick with each other. And they have a wonderful social structure where they don't fight as much as chimps, which are like the opposite and male-centric kind of battle bots. So imagine you upload a primate, bonobo, let's say. The pace of silicon progress would be so great that by the time you wouldn't bother to reverse engineer it, you wouldn't bother to say, well, what worked, what didn't. You just start to run the silicon faster, and it would, could very well be the AI that takes over wouldn't even be human based for that reason, because the sort of race condition, by the time someone gets around to uploading human, it hasn't had time to catch up. By the way, this was an interesting little time capsule from 2007. For those who just don't realize we're like state of the art today on attempts to unify some of these things. Let's say evolve for purposeful outputs. But Koza has gone more into politics of late, but he was breeding programs for quite a while and found that Any application space where it's very easy to validate if you have a good solution, but very difficult to think of the solution, like analog circuit design, antenna design, it lends itself great for these kinds of algorithms, right? And so what he did is he bred programs to build, and some of these have flown in space, an antenna that flew in space, and it was this cockamamie thing, no one understands why it works, but it was the best antenna for a given need, or analog circuit design. And he's already gotten patents on these. So, back in 2007, he was just starting to get patents that he was reproducing many U.S. patent, sort of human patented inventions without any input. Just, here's what the filter needs to do, find a filter. But then he got new designs that were actually winning patents as being novel. And he was believed in this domain. He was routinely delivering human competitive machine intelligence. Another example that I like, it's one of our companies, is the way in which you can design for evolvability. And this will be the last example that I use. Imagine you're trying to, again, back to synthetic biology, build an organism that does something useful. And the most common example is make a chemical you want. In this case, it was butanediol, which is the major precursor of spandex and automotive plastics. So the spandex of the future may be built from sugar and maybe green through their work. So the goal is, how do you make a microbe, and this is their metabolic pathways shown here, do what you want. So they started off with simulation tools. They simulated all of 40,000 different pathways to get from A to B, and analyzed mathematically and engineering sense, what is the most carbon efficient, the most sort of efficient use of energy, and then one design team was working on that and got about a 5-fold improvement in the yield, making the chemical they wanted from the start. And by the way, the chemical is not made in any organism naturally. It's a completely synthetic pathway. A different team in the same company instead selectively crippled the organism. And they didn't pick, for this design, they didn't pick the most efficient pathway through. They picked one that would allow them to knock out all the other pathways of survival, where it can't eat a variety of feedstocks, it can only live on certain sugars. It's an incredibly weak, poorly suited organism to live. But it happens to make the chemical that you want as a byproduct. And instead, they just skimmed the fastest growers over 3 months. So take whatever organism is growing fastest, put in a new beaker, give it another day, put that in a new beaker. And after a few months, they had improved the chemical yield 20,000-fold. So human design, 5-fold improvement, random search, 20,000-fold improvement. They have no idea why or how. But what's interesting is they don't need to. And the process may keep improving even as they scale. So one of the problems with synthetic biology is you have a lab scale demo where the surface area to volume of a beaker is different than the surface area to volume, let's say, of a huge tank. And all of a sudden the process falls out of bed when you try to scale up some, let's say, yeast fermentation process. And scaling up in biochemicals and biofuels has always been a risk factor that scares people. Well, with this evolutionary approach, in a way, if temperature varies, if the environment varies, they get better and better over time. So it's not just like over 3 months they got a 20,000-fold improvement. It got better a month later, and so on and so forth. So it could be more robust, resilient, and capable of deployment. I'll just end with one quote. Danny Hillis, on his last page of his computer science summary book, believes that the greatest challenge would be to create tools that go beyond engineering to create more than we can understand. And also Kevin Kelly, I like that we are in fact evolvability. I'll leave it at this. I'll go to Q&A. I'll just leave these 4 bullet points up there to say that if you think about how you manage people, actually I'll just make these 4 points and then be done. If you want to exploit the wisdom of crowds to be innovative as an organization, there are certain policies you might want to consider. Like diversity is more important than ability of the individuals. This all falls out of the same analysis and genetic algorithms and such. The disagreement in a team about a topic is more important than reaching consensus if you want to find disruptive change, innovative change. Your voting policies, like what does it take to commit resources to a project or not, is more important than having any coherence or comprehensibility of what you're actually doing. And that the function of management is to tune the parameters of communication. Things like, when do we meet? How do we communicate? What's the fan out? And most importantly, what's maximum group size? Teams of 3 to 7 get stuff done. Everything larger than that, productivity goes through the floor. That's more important than direction setting. It's not leaders doing their symbolic leadership stuff. It's setting up the parameters for a hive mind to emerge in an organization. So what have I tried to share with you today? I think accelerating technological change continues forever. It's leading to an interdisciplinary renaissance of learning, which is fascinating and exciting to just be a student of. And now is reaching trillion-dollar markets where it hadn't before and revolutionizing them, energy, fuels, chemicals, and such. And that it is the perpetual driver of disruption, the thing you can count on 50 years from now to create new entrants, new entrepreneurs, and therefore a good time to build new companies. So for example, if this isn't obvious, let me make very tangible in a Google example. I do not believe Google will ever reinvent search. I don't think Google would ever be expected to disrupt search marketing or search as it exists today. You would never expect Google to do that. To reinvent the data center and how computers are built? Absolutely. Right? In terms of radical change. to punt on ever using an Intel chip again. Google could absolutely lead the charge there. Just like in music, right? Apple was a new entrant with the iPod and iTunes, right? It wasn't going to be Sony. Sony would never revolutionize the Walkman. It took a new entrant. New entrants can be big companies like Apple. So, and again, if you want to think of where these theories apply, it's not to anything having to do with search. And I think the technium, as Kevin Kelly calls it, is moving increasingly from design to search. So on a positive note, concatenating code that exists is, I think, going to be the paradigm of the future, not designing new code. So let me leave it at that, if we have time for questions. Thank you.
Thank you, Steve.
We have 1 minute. 1 minute for questions.
We have run over a little bit, but we're willing to take a couple questions.
Leave this up there.
That was really interesting. With all the talk of technological progress increasing in speed and everything, how concerned are you about, the technological singularity where we become unable to predict the future or model our future because of things that are smarter than us in charge?
Right. That's a good question about it's one subset of the risk of a singularity. Other people are scared of it. This sort of, for those not familiar with it, imagine the exponential does continue forever and never becomes an S-curve. What is the sort of ultimate endpoint of that completely life-changing event? Ray Kurzweil writes about this quite a bit, where perhaps, all matter, gets recompiled in some new computronium in the future. Just really crazy, out-of-band thinking. When I say crazy, crazy to our thinking, right? So again, all great ideas are considered crazy, so don't take that as a negative. But specifically, this idea of us not being able to understand it may necessitate the AIs that I was describing. That we may in fact need to birth technologies that can assist us in this. And in fact, we may not even need to do that, right? There's some who argue the internet's already got all the attributes of a living organism, that all attributes of life, and those who study the internet in its totality have to resort to the kinds of techniques that biologists were using, not the techniques that computer scientists were using to sort of make sense of the patterns. So let me phrase it in a different way. If someone were to ask you, would you want your great-grandchildren to be smarter, healthier, and more capable than yourself? Yeah, that sounds good. If instead you say, hey, there's going to be machine intelligence next month that's going to be healthier, happier, and more intelligent than yourself, that feels threatening, right? And most sci-fi novels are based on it. But I think once we shift our sense from an entitlement that humans are the endpoint of evolution to a sense of parenthood, that we're going to create something greater than ourselves, then we could actualize our universal quest for symbolic immortality. I think every human wants to be symbolically immortal, meaning they create something that outlasts their short time on this planet, a work of art, their children, most tangibly, a company that will live on past the founders, Hewlett-Packard being, a sort of easy to remember example of something like that, or a belief in the afterlife if all else fails. And I think creating those artifacts will be one of our most powerful vectors of being transcendent. To say, we didn't end evolution through some clinging motion to say, God, it has to include us. Hopefully, it'll find some way to include us. Will it be augmented intelligence or artificial intelligence that we create? I think that's a profound debate. Here's one more. Maybe that'll be the last question. Okay, last question.
So you had one slide about managing disruptive innovation, and you kind of mentioned the challenges of getting 2 or 3, the teams of 2 or 3 people are very efficient, larger teams aren't. Right. What do you think about the challenges of innovation in social technology to allow us to get more brains working on the same problem in parallel? I feel like there's a lot of opportunity there that's kind of outside this whole branch of physical technology. What are your thoughts on that?
I think it's a great question. Because clearly, historically, in meat space, it's physically getting together for meetings, that was the metaphor, not virtually, and to do so on a lightweight, periodic basis. So let me first say a little bit more about the group size and then see if a thought occurs to me, because I don't have a quick answer other than, yeah, that sounds exciting, and I'd love to hear what your thoughts are on it. Because as a backup, venture capitalists almost never come up with an innovation or an idea or the solution to a problem. But what they try to do is recognize big problems, and when some smart person does, to glom onto it and say, that does sound like it could work, and so that's where my mind goes. So I don't know the answer to almost any useful question, other than the sheer enthusiasm. So actually, I would say groups of 3 to 7. So boards of directors, as my experience, more than 7, they're horrible. I do believe there's some attempt to try to keep programming group size down low here. I 2 weeks ago had a whole weekend with Bill Gates, which was fascinating, and he was just sort of off the record on all subjects. Unbelievable. But one of the things he did share, which no surprise, is that he thought Microsoft has never been as productive or as fun as when it was 5 people. And he thinks they're just a complete train wreck right now. No surprise. So at least he's honest now. He's not in the corporate, veil. He can speak openly. You get this dramatic. You end up inevitably putting in policies that migrate to the mean. You don't have outlying experiments running on, and it gets difficult in some organizations, by the way, to keep doing that. So, like Gore, a manufacturing company, actually physically moves manufacturing plants when they get over 150 people. And think how expensive that is for a manufacturing company. But the logic is no one knows the name of their coworkers beyond 100. That's where startups usually hit a major growth curve. A growth hiccup. Is sort of when you don't know the members of your tribe in the same way, your management style has to change, and then it gets very unpleasant as a transition. So back to how can social software help with this? I'm a big believer that we have really barely scratched the surface of how to exploit the hive-like mind in an organization. Right? For a group of people to be more productive than the sum of its members, there has to be something going on at that higher level of abstraction that allows that. And so the questions I would ask is, what should be the frequency of interactions? What should be the fan out? Should it be bidirectional information flows or not? If you think about a cortical analogy, the fan out has a dramatic impact on learning phases. And you may want to prune. You might want to have, like the brain does, 100 synapses per neuron dropping, tenfold in the ages of 2.5. Actually, 10,000 synapses per neuron dropping to 1,000 between the ages of 2 and 3, which is kind of interesting. You lose 90% of your synapses. Those kinds of parameters could have a huge impact on it. And I generally think the best answer could be to run experiments, because whenever you get into the social sciences, I think you can run experiments in organizational form much more quickly than you can formulate the theory for why they work. Yeah. Cool.
Great. Thank you, Steve. I appreciate you taking the time for a talk here at Google.